Hey everybody, I wanted to sneak on before the actual start of our video just to give a little bit of homework help. I do recognize that our current lab is a little bit more challenging than some of the previous ones, and so I do think some of this help will be useful to you because I do try to give you guys good, helpful advice. So a little bit of homework help here. For our current lab, it is a challenging lab, more challenging than I perhaps intended. So some of this information I've given on D2L as a news item, so I'm just going to briefly cover and discuss some of it. Some of it I'm not going to explain in great detail. Some of what I'm giving can be thought of as kind of hints and clues, and you can use this and figure out exactly what I mean. So if you do your virtual protect, it'll do one of two chains. The one I want you to use is this chain right here. So you need to, and I really can't think of another way in which to do it. This one right here uses a different chain, and so we have a jump EAX. And the jump EAX, we follow this along, goes into ESI, and that is going to be our way of dereferencing our virtual protect. If we go over here and we do it this way, we need to do it in a different fashion. So I mentioned that we want this to be our push ad. If you look for push ad in SkinMagick DLL, you're not going to find any. That means it needs to be, make sure this is the right amount. Yeah, one of the 400,000 address range is where it's going to be. The problem with that is it's a no byte. So if you have that on the stack, then it's going to stop. So you can't directly put that on there. However, what you can do is you can use other registers, other instructions to manipulate the values so that you get, let's say that this right here is push add. It's not, but let's pretend it is. And I get this as a result of maybe add EBX, EDX, whatever the case is. And so now it's in EBX, and I can somehow get that EBX value over to EAX. So maybe I do move EAX EBX. Of course, there would be a ret after each of those. So these are separate gadgets here. So if this was my push ad, then I can use other registers, other instructions to manipulate them such that it has that no byte positive push ad. Here it's an EBX. I take EBX, I move it into EAX, and now it's where it needs to be because it needs to be here. Instead of doing the NOP, I'm having you do the push ad. Now, if you do that, it's going to create another problem because when you push it onto the stack, it's going to push that push ad onto the stack. And this is one of the ones where it'll make more sense once you do it, and it's one of the ones I want you to kind of think about and kind of figure out. So I'm telling you this because I know that if I don't, 95% of you are not going to think of this. But instead of having the return be automatic, we're going to have it be a pivot. So we can pivot over our push add. So in order to do that, we can just add to ESP some trivial small value. And then from there we went to get into our NOP sled, which you should understand at this point what a NOP sled is and where it fits into the grand scheme of things. So those are a couple things to be aware of. Another thing that we need to be aware of here is that some of you may figure out, but others of you may not, is we have a pointer to Virtual Protect, and it's going to be, say, 1024, some address like that, belonging to Skin Magic. I'm on a new keyboard here, and the home and in button have changed, so I'm not quite used to that yet. Because I actually do use those keys very frequently, usually. But in any case, this will point to the real location of Virtual Protect, which will be in kernel 32. And so if we were to do jump EAX, and EAX has the pointer to this here, that would then go and dereference it. Here, instead, I'm going to have you dereference it yourself. So how do you dereference it? You know, we can do something like move EAX EDX. That would dereference it. So if right now EDX had my Virtual Protect, that would dereference it, and that would get the address in kernel 32, which would be, let's say, making this up here. So this address, this is a pointer to the kernel 32 that's inside Skin Magic. And then once we dereference it, so we would take this, place that into EDX, and then we get this value over in EAX. So we've dereferenced it. Now when you go to try to find that, you could do a find wild, although the syntax has to be correct, and there are variations when you're writing an assembly on how you could actually do it. Or you could open up the ROP.txt where it has every ROP gadget, and you could just do a find at the bottom, searching for that. But if you have something like this, that would do the trick. So that could be something to maybe check out. Once you get that, though, so this is not going to be straight, easy 1, 2, 3. You're going to have some more than one gadget going from place A to your final destination. And that does get to be somewhat challenging, because at the end of the day, it needs to be an ESI, so you're limited to some extent on what's available with ESI. I will give a hint, just because I know this one is challenging, is one way in which you could transfer something is if you do a push onto a stack. So if I have it in push EBX, which I don't know, let's assume it's an EBX. So push EBX, and if I had a ret, then the next thing that would happen would be that this would be executed. I don't want that. I want to load it into ESI. Because of how that works, once you do the ret, this will be on the top of the stack. It'll be what's next. So you could have another push. So you could do, push EDX, and then it would go there. Actually, that probably wouldn't work either. So scratch that. So what you would want to do is instead have pop ESI. So we would do the push and then pop. So it was an EBX, now it's an ESI. It's no longer on the stack because push will put it onto the stack, and then pop will take it off of the stack and push it into, or pop it into ESI. So this is one way to transfer something from one register to another. I haven't mentioned this before, so I wanted to draw your attention to that. So you could go to your ROP.txt and you could search for that, or you could be creative and try to do a find wild on it. Remember, with the find wild, you can do things like R32 for any register, or you can also do like this if you want a wild card. So if you knew there was going to be some other stuff going on here, you didn't care what it was, or some stuff going on from ESI to the end, that could be something you could do. But in this case, your final destination would be ESI, so you wouldn't want to do R32. Just some little tips there if you wanted to try to do the find wild to do that. So in any case, I do recognize that this particular ROP exercise is a little bit more challenging. And so that's why I'm giving you some more clues. For most of you, this is your first ROP exercise, and there's enough complexity that most of you probably wouldn't figure that out on your own without a little bit of help. So welcome everybody to our next video. Today we're going to continue to learn a little bit more about shellcoding. So we're going to learn specifically what we need to do in a Windows environment when you're shellcoding so that you can get the API addresses that you need. Those of you who've had me for a reverse engineering course, this is not new information. So you may not necessarily gain a lot from this video, but our next video we're going to take some of this information and then go forward with it. So please be patient, and we'll get this foundation built, and then we can use that knowledge to create our own shellcode, more complicated modern shellcode. And then really the sky is the limit in terms of what we can do. And I've seen some students create some truly outstanding shellcode, so I look forward to seeing what you guys come up with, which will be part of your next lab. So, all right, let's get on with it. So part of understanding shellcode, particularly in a modern Windows environment, has to do with figuring out how can we gain access to libraries, to modules, to DLLs, which all three of those words mean the same thing. Not only how can we do that, but how can we at runtime then discover the address for certain APIs or functions that belong to these different libraries, DLLs, or modules. As we saw in our previous video, when we use our shellcode, it's position independent. We don't know the address of kernel 32. We don't know the address of NTDLL or any of the functions that pertain to those libraries. So our solution is to call them up through runtime. We can do this firstly by walking the PEB, and then from there we can walk the PE file format. So what does all of that mean? For those of you who've had me in a reverse engineering course, you probably know in very, very great detail what every step means, because you've gone through and you've done it all and discovered all that information on your own. For those of you who have not, maybe you've encountered it in malware, because this is a very, very widely used technique that we see in malware. Certainly, if some of you are taking the .troll malware course from Dr. Strohschein, or have taken a malware course from me, you will definitely encounter this. So this is going to be the method in the modern Windows shellcode where we can gain access to those, and once we've done that, then the sky's the limit. But if we're doing it in a shellcode type situation, we are definitely forced to do it this way. No choice about it. The only other option is if you want to go back to, say, Windows XP, Service Pack 2 or 1, or then maybe you could do it the more old-fashioned way where there's a preset address for functions because ASLR is not in place. ASLR is pretty prevalent, so we need to address that, and it's just the reality. And we'll see that some of the stuff we go through here today is maybe a little bit complicated, but it's nothing we can't handle. So I have a program, a C program, and inside there is inline assembly. The inline assembly, we can think of that as our shellcode. In a later video lesson, we'll learn how we can more directly create shellcode. So this is kind of an intermediate to shellcode, but that's okay because ultimately, when it gets to this point here, it's executing it is shellcode. Just pure assembly instructions. So let's talk about what our first step needs to be. Our first step needs to be we need to gain access to the process environment block. What is the process environment block? Well, let's look that up here. So I brought up process environment block, the PEB. So it's a data structure in the Windows NT operating system. So very elaborate data structure. Contains all kinds of relevant information that can be incredibly useful to us. So some of the fields here being debugged, LDR, process parameters, some additional fields there. Now what we ultimately are going to be interested in is the PEB LDR data structure providing information about loaded modules. Now in order to get to the PEB, we need to start somewhere else. That's the thread information block, the TIB. It's also sometimes called thread environment block, so either way is the same thing. And this is a somewhat elaborate data structure, another very elaborate one. And there's going to be variation based on Windows 32, Windows 64. So FS, if you see that, is 32, GS, it's 64. And so just like with the PE file format, it's just a series of data structures in fields. In this case, it's fields, and within these there can be other data structures. We start at FS0. That also points to the SEH frame, structural exception handler. So when you do your EX chain, it goes in there and it extracts information from this location. You could do that directly yourself by doing dd fs colon x0. That could be something you could do. I think that EX chain presents it in a nicer format. And some various other structures. But we're interested in one very specific one, the PEB. So FS as well as GS are both registers. So if you didn't know that the FS register existed or GS register, well, guess what? They do exist. There are a number of various smaller registers that we may not think of or encounter typically. And this is one that is used by the operating system to connect to the TIB. So all this important information is going to be immediately available, and we can access it by making use of the FS register, or GS if we're 64-bit. And this really pertains to not your operating system, but the application. So every application we've looked at has been 32-bit. So in any case, we want to get to the FS30 or FGS60 if we're 64-bit. So in order to do that, we will, because right in here will be a memory address for the PEB. So in order to get that, we will need to dereference FS30. And then we will know the address of the PEB. So we just take it one step at the time. Let's go into our WinDbg here. That's not what I wanted. I guess I haven't opened it. And we'll go into shellcode. So DSFS0 is our SEH. I don't really care about that. I didn't actually mean to type that, it was just on the mind, I guess. Right here is our PEB. So that's the address of the PEB. I could also use some WinDbg commands, and that gives me all kinds of information on the PEB. Don't get too caught up in the WinDbg commands, because when you're doing actual exploitation, you can't just issue a command like this and magically take information out of it. You need to get that information by traversing it, by walking it through assembly. So I know that it's at this offset. So I got to think, how am I going to turn that into assembly? So I want to dereference this and then move that into another location. And one way in which we can do that is just move EAX FS30. In this case here, this probably is not a good one. We probably would want to, and I've already alluded to this before, because doing this will introduce no bytes. If I do FS EAX plus 30, there won't be a no byte. I would want to XOR EAX first, so it's zeroed out. So this would be an improvement upon that. So if I follow this here, I can follow it, and now I can see various other offsets. Now what I'm interested in next here is, let's return to our page. So we're done with the thread information block. We didn't need very much from it. We just needed one thing, the FS30, and that gets us into the process environment block. Well, now I'm interested in the LDR, the pointer that gives us information about loaded modules, or another word for that is DLLs. Because I want to get in there and I want to find the base address of different modules. I know that there's a guarantee that kernel 32 and TDLL will be loaded. Absolute guarantee. There's no guarantee about any other module or DLL. I mean, it could be if you know the specific application, and you can open it up and see for yourself what modules are loaded. But if you have no knowledge of that, then you at least guarantee that those two will be present. But this structure gives me more information about that. At this point, maybe we don't know about this because it doesn't tell us anymore, but I know I want to go here. And so this source here probably is not a good source for us to get the information. So we'll turn to MSDN. Process environment block. And so we can see LDR there, some reserved ones, which we don't know what those are necessarily. Although if you open it up and look at it inside WinDbg, then WinDbg does give some additional information if you know how to do that. We want to get to this. What is this? We can go learn about that here. So this gives us information on eventually some reserved ones here, and in-memory order module lists. So those are things that I would want to potentially get to. Now let's not get too ahead of ourselves here, because we need to figure out how to get to the LDR. So how to do that is we just simply count the bytes. So I see 1, 2, 3, and then so 3 here, and then 2 p voids. There's 2 of this here, so that's actually, let's start over here. So 2, 3, 4. A D word, a p void is going to be a D word. So we're at 4, and then we do 8, and then 12. And so 12 is going to be decimal. We've got to think hex. So that would be C. So let's go check out our code here. And that is correct. So I dereferenced this. I got that address that we saw and moved that into EAX. Now I'm at that particular location. And from that offset, I count 12 bytes. So a byte is 1 byte. We got 2 of them. Got another byte here, another byte here. P void is a D word, or 4 bytes. I got 2 of those, so that's 8. So we just get to a particular location in memory, and we just add 12 bytes or C bytes in order to get to the next location, and that next location will be our LDR. So that's how that works. So we want to get to the LDR. We determined it's C, hex C. Well, what is the LDR? We read that it, so structure has information about loaded modules. We can follow that link and we can learn more about it. So Microsoft will be our definitive source, one of the definitive sources of information when it comes to things like the PEB or the TIB, because they're Microsoft specific. Now Microsoft is kind of stingy about the information it gives. Some of that information is internal, so we see things like reserved. They're not telling us what that is here, although if you use some of the defined structures in WinDbg, then they will tell you. But right here, they don't. So in-memory order or module list, that's one they do tell us. And then we have a p void. So if we go down here, this lets us know that this is the head of a doubly linked list that contains modules for the process. Each item is a pointer. We can see information on the flink and the blink. Now, understanding the flink and blink is going to be essential if you're trying to reverse this from scratch, because these are going to be linked lists. So learning how to navigate those will be important. And then eventually we can get into LDR data table entry. I'm going to turn to some slides I have here that I think may make this a little bit clearer. So these are some alternative sources, non-Microsoft. So I can decide, do I want to go inside one of these? So different module lists. What that means is they're linked lists that contain information on different modules or different DLLs. And depending on which one it is going to be the order in which they appear. So in initialization will be different than in load. So if you're reversing this from scratch, understanding that and the order in which they appear is going to be part of the process. So as you do this, you probably are going to think, okay, I want to do kernel 32, I want to do NTDLL. Those are going to be the more common ones. And the example that I'm showing you here is going to be kernel 32. And there are alternate ways you can do that. So kernel 32 will appear in all of these lists. It's just that it'll be in different order. So you need to know the order in which it appears for the module list that you look at, so that you can then navigate to it. In this example, we can do 1C. So let's go back over here. 2. 1. 2. 3. 4. 5. 6. 7. 8. 9. 10. 11. 12. 13. 14. 15. 16. 17. 18. 19. 20. 21. 22. 23. 24. 25. 26. 27. 28. 29. 30. 31. 32. 33. 34. 35. 36. 37. 38. 39. 40. 41. 42. 43. 44. 45. 46. 47. 48. 49. 50. 51. 52. 53. 54. 55. 56. 57. 58. 59. 60. 61. 62. 63. 64. 65. 66. 67. 68. 69. 70. 71. 72. 73. 74. 75. 76. 77. 78. 79. 80. 81. 82. 83. 84. 85. 86. 87. 88. 89. 90. 91. 92. 93. 94. 95. 96. 97. 98. 99. 100. 101. 102. 103. 104. 105. 106. 107. 108. 109. 110. 111. 112. 113. 114. 115. 116. 117. 118. 119. 1 Well, actually, I guess in this example here, they do the first one, so they do C. But they could have done 1C. So just different way of doing that. So in this example here, we see the code is 1C. And then this right here, and this part here is just kind of confusing for a lot of people to understand. But you do a dereference, and then you can move past the first one. You do a dereference, you move past the next one. You do a dereference. And so that's just a way to progress through the linked list. And then right here with the 8, then they're going to the DLL base, which we saw the DLL base. Is it on here? No, it's not. So let's go back to... So the DLL base is going to give the base address. And I guess it doesn't tell... If we look this up elsewhere, this will tell us. This gives us the base address. So if I'm looking at kernel 32, I'm looking at NTDLL, this will give me the base address, meaning the starting address for that. So that's very important, and we'll see why in a moment. So being able to find just this, then we can go from PEB to PE file format. So one way in which we could do that, this is one example. This is an example here of kernel 32, where we're doing the first link data structure, and then we follow that to get to the third entry of kernel 32. Then offset plus 18 to get to the DLL base address. Just one way of taking into consideration the flink and the blink, which we're just kind of glossing over that here. And then we can go back to my slides here, and we see an alternate way of doing that. So we do 1C, and we're just doing it in this fashion. Same thing, it still allows us to get to the DLL base. And you might be wondering, well, why do I care about the DLL base? I mean, what's the big deal with the DLL base? And the reason for that is we get to the DLL base, then we can get to the start of the module. The start of the module is going to be something very special. So what I'm going to do here is, and we'll find out what that is in a moment here. Int3 is an interrupt, so software level interrupt. So if I do that and compile this, it should be open. Need to close out of here. Then go ahead and open this. And hit G for go. And I'm not sure what's going on here. It's stuck on busy. But now it took us over here. So finally at length it got us there. And let's go revisit what the code is here. So after this instruction, then supposedly EAX will then have the DLL base. Okay? So right here. Let's go ahead and do that instruction. So I've done that instruction. And what is there? Well, I can do DA on EAX. And what is that? MZ. Or if I do this, then I have the 4D5A, which, with little Indianness, the 4D5A. The MZ is our file format signature, the eMagic. This means this is a PE file. So if I can get to this location, then I'm done with the PEB. Now I can treat this as if it were a PE file format. I can traverse the PE file format. So very similar to what I did, just different structures now. So gone all over to 010. I've went and got a template for the PE template, and I've ran the template, and so now I can apply the structure. So I'm right here. I'm in my copy or my original one without the interrupt. Because if you have something like the software interrupt like this and you run it outside of a debugger, it's just going to stop. It's going to give you an access violation. It's done. It won't go any further. This is only for that you use in a debugging environment. But in any case, I'm right here, and I can use my knowledge of the PE file format to get to where I want to be. So I'm right here, and my next step is I got to get over this nasty DOS stub so I can look for the LFNU. So LFNU will tell me the offset that takes me over here to this location. And so that offset, the LFNU, is going to be at right here. So this is the LFNU. It starts here. So this is the first one, second, third, fourth. The F8, and the F8 takes me right over here to actually right here. So F and then 8, and so it takes me to this signature. And of course I can visually see that because I'm familiar with it, but if I didn't know that, then I could have just gone like this and went down over to LFNU, and so it makes it very obvious. So if I get that, because why do I need the LFNU? Because this DOS stub is variable. It doesn't have to be this. It could be something slightly different, and so the bytes would be different. That makes it hard. If it's not a constant, then we need to take that into consideration, and so LFNU is our way to take that into consideration. So that then can get us over here to the PE, which we go into our NT header, and then from there we can go into the file header, and then eventually, which I meant to click on, the optional header. So we want to get from right here down, keep on going down, get into our data directory, and then we want to get to our exports, and then we want to get that virtual address. So lots going on there, but we got to do it one step at a time. So we're at MZ at the end of that chunk of assembly, and then we need to find a way to get the LFNU. So how do we do that? So right now the MZ is right here into EAX and now EDX, which they're saving to use later. And so if we do 3C, that will give us the offset for LFNU. Let's count 3C. So we just start from our starting location right here, and we just count 1, 2, 3, 4, 5, 3C. And so we take that, we do EAX plus 3C, that gives us that offset. We're doing dereferencing, meaning when we do a dereference, we say, here's the memory address, give me what's inside of it. So we don't care what the memory address is, we want to know what's inside that memory address. So we dereference that value and then move that into EBX. So right now EBX has the value of F0 or F8. And so I can take that and then I can move that into ECX. We're just saving it there. And then we add ECX to EAX. What is EAX? EAX is the start of the MZ, the start of the PE file, the memory address for that. So the memory address wherever we are in memory. So we can add, right now we're adding F8 to that. And so when this instruction is done, we will then be right here. Then we can this then allows us to get to the image directory. So if we follow that along, we get past this, get down over here, and let's go over here to our structures. So if we were to count from right here, offset 0 down to hex 78, that would take us right there. Gets us to the start of the image data directory. And the first value inside there is the virtual address. So this is offset 78. This is also offset 78. This is also offset 78. And we can see the size there. So 4 hex, 8 hex, 4 hex, etc. Okay, so let's try to make sense of what we've been doing here. So we go and get our LFNU, our 3C. We calculated that. We add that to our base. We dereference that location, so we get the value that's contained there, which is an F8. We move that to EBX. EBX now has the LFNU value. We move it to another register called ECX. So ECX now has our LFNU, and we take that value and we're adding it to EAX. EAX again is the MZ, the start of the PE file format. So we have our MZ up there, and then we add our F8 that we have right here, and then that takes us again over here to this location. So we're just counting the distances and using that to navigate the PE file format. So now we're right here at the PE. We want to get down to our data directory, the virtual address. And if we calculate that distance from here to here, and you can do it, you can count the bytes, it's 78 hex. So we take that and we add that to EAX. So the memory address there, we go ahead and add that there. So that gives us the memory address, so the place in memory where that value is. I mean, the memory address is nice, but we're a little bit more interested in the actual value that's in there. I don't care where the memory value for virtual address is. I want to know what's inside the virtual address. And so I take that, and now EAX has that address, and this is just a kind of a funky way of doing it. There are more direct ways, but hey, it works. And we dereference it, and so now it's in EBX. So EBX is our export offset. So that takes us to our export table. Because we want to get down here, this right here is our exports directory. That is our end goal to get there. So we get the virtual address, and we dereference that. That gives us the offset. And then we can take that, add it to EAX, which is the DLL base. So the virtual address, I mean, the export directory is one of those things that's variable. So it's kind of like LFNU, where there's no necessarily guarantee where it's going to be, so it kind of involves a jump of sorts. And so that's where the virtual address comes into play. And so that's why we get that value, we dereference it, we add it, and then now we're at the exports table, which we kind of alluded to, but we haven't really talked about. And so this is the exports directory or exports table, and there are a number of different functions in here. Right now we're interested in the number of functions. It's going to tell us how many functions or how many APIs are in the DLL. We care about this because we want to do a looping mechanism where we can basically have a counter we can go and search for something, and we need a value for the counter. This is our value for the counter, number of functions. Number of names is similar, but different. So we go ahead and we can, I'm on the wrong OS there. We can count the values, and if we do that, then it turns out that it's 20. And so we move that over there to 20, and we get the value for the function of names. Once we do that, then we can dereference that to grab the function name offset. So we're concerned with the value inside there. We move that to ECX, and then we add that to, we restore the DLL base, and so we add that over there, and now we know the value that's in there. So say there's 1,920 or some random value. Now we have that value for our counter, and we can save that and utilize it. And then from there, we can break it down into, we do a search to try to determine the address of a specific function. So in this case, we're doing a search for alloc console. So once we get past that, then we want to use, we have our counter. So we also need to take into consideration a few other things. We have our address of names, our address of functions, our address of ordinals. We can use all of these together. The trio is a means of iterating through the different export names. So address of names will provide us with pointers to the ASCII strings that are going to be the export names. So that's why we care about address of names. We can also use our address of ordinals value as an index into the address of functions array. The address of functions array is what's going to have the address of the function. So where in memory do we go to get an address of the API? So again, three of them: address of names, address of functions, address of ordinals. Or address of names again gives us the ASCII for the string. So this right here, I would go in there, I would use that, and then I can use, these are to some extent they're parallel arrays. Once I find that value, say it's 500, then I can take that 500 value and I can insert it into address of ordinals. The address of ordinals will give me a value that I can then make use of in the address of functions array, which then can give me the actual API address. So here there's a comparison loop. We use our CLD, and then we're clearing some things out. We do rep compare string bytes. So we're doing a comparison of strings byte by byte. And then repetition, meaning we're going to go through these, iterate through them just one at a time. And so this is a very special assembly instruction that is used to find strings. You know, if you have a particular string then that you're looking for, this is the assembly instruction that's designed to make use of with that. Now, when you have rep compare SB, there are some other things that come into mind. So the CLD is going to make sure that the rep works in the right direction. That's really all we need to understand about that. We also have ECX, so that's going to be our counter for the number of times that this is going to search. So this one is set to search for only 4 bytes. I guess this must be the first one that has ALLO, or maybe it's the only one, and so that's why it only goes that far. But you could go further. Going further probably would be better. And lost my place here. So that's that. And then we also have ESI. So ESI is what we're searching for. So the letter. So we're searching for letter A. Actually, no. So ESI is going to be the element in the array. And then EDI will then contain the string that we're searching for. So we do a search. We do it just one letter at a time. If there's a match, then we have the JE, so we can jump over to the match. If it's not, then we add 4 to it. 4 because it's a D word. So we're progressing one more to the next value. And then we also have a counter too. And this counter allows us to establish am I in position 500, am I position 535, etc. So that once we finish, we get our match, we know which position in the array it is, which element, position 500, position 700, because I need to then use that to get it in my parallel array. So I can take that value and then I can use it in my address of ordinals. So, you know, it is important for me to know that and to be aware of that. So that's the comparison. And when we get a match, now the counter is pointing to the correct value. So we go down over here. And these things right here, right now we're just dereferencing the offset for ordinals. So that's what we're doing there. Then we get our counter value, and we use that counter value to get, so this is the offset of ordinals. We want to use that counter value that we establish up here so that we can then go in there and get the address of ordinals for, you know, say position 500. This was a D word. This is a word. So that's why they're different. And that's something that really gets a lot of people. They don't notice that. And so if you don't notice that, then, you know, that can create some problems. You know, we can multiply by 2 to account for the offset. And then right here, we're just going in there and dereferencing, getting that value contained at that offset. And I am going through this part a little bit fast, not spending a huge amount of time on each and every instruction. But certainly feel free to pause it and contemplate it if you need to. So right now we're just going in and getting the address of the function. The address of function. Where is the address of function in memory? Once we do that, then we can get the offset there. So this here is just a really roundabout, slightly indirect way of going and getting the address of a function. So you can calculate address of function, the ordinals, and the function names. And then we go back down here and we get that, we get the value, we dereference it, we add it to the base, and then eventually we get the offset, so the value that's and then going to be in there. And then the rest of this here is just finishing it up, dereferencing it, and skipping over some stuff here. But at the very end, it's going to allow us to point to the requested function address. So that's an EBX. We can then dereference it. We get that value. We add it to the base. So the base of our kernel 32, which is what we're looking at. And then now at length, EAX then contains the value of this. So that's one way to do that from an assembly standpoint. There are some other. Once you get to this point in the code, there can be some variation in terms of how exactly you do it. But at the heart of it, we're using a few things. We're using our counter, we're using our address of names, our address of functions, and the address of ordinals. Eventually we get the index that we want from address of functions, and it points to. We can use that inside of our address of ordinals to reach the API address. So this is one way using shellcode, which this is not exactly shellcode. It's assembly, and it's pretty close to shellcode. We could do some slight changes. And this is again being done as inline assembly inside a C program. So the final result here is it would give us that address. So let's go ahead and comment, or just not even comment, but let's remove that. No, thank you. And we'll close out of this. And then the wrong one there. So go back over here. And so that has found the address. We can go down to this little chunk right here. So the first thing it prints out is this right here. It found the address. And then now this is utilizing Windows APIs. So we can use the Windows APIs inside of C. So we've talked at length about load library, get proc address. We load kernel 32, and we get the address of a particular API. And it gives us a result. We print that result, and we do a comparison, and they're identical. And so this is a somewhat trivial program, or shellcode, but it's something we see repeatedly in exploitation, repeatedly inside malware, because this is the process that we need to do in order to get an initial API. Well, what if instead of doing this, I instead searched for get proc address? I'm in a shellcode, my kernel 32 is already loaded. Now I have get proc address, and I can use get proc address to call and get the address of any other function that exists inside of kernel 32. Load library is part of kernel 32, so I could also, once I have the get proc address, I could do load library, and then I could use load library to load any other DLL that I want. So if it's not something that's currently loaded, but it's part of the Windows package, I can load it, and I can have access to all of those APIs. And then it's just a matter of doing API calls, which right here, this is a C way of doing our API calls, but we can also do that through assembly, just like you're doing with your ROP. Of course, it's much easier to do it in assembly or in a shell code. So Today we're just trying to get our head wrapped around what's going on with this. Now, some of you have had me for reverse engineering. This is just review, and it's probably boring you to tears because a lot of this is ingrained in you, and certainly there are different variations on this, even techniques. Very rarely do I see different variations, but sometimes there are some very unique variations. But by and large, this is a common approach. Now, you will be writing more complicated shellcode and utilizing it. It will be coming up in your next lab. It's not going to be this week. People are struggling with ROP, so we'll wait till next week to put that out, but it is coming up. So, keep that in mind. Am I going to expect you to do this all from scratch? No. I'll provide you with something that is similar but different, something that was extracted from a piece of malware, and very nice and very clever about the way in which they can make use of different things. Like, we get started here, and then we can start to load other APIs, and the way in which they do it is they do it through hashing. I'll provide more information on that once we get there. I do hope that everybody is able to stay home and stay safe during our present pandemic. I know these are challenging times. Hopefully our activities in this course can provide you some fun as well as some enrichment, and certainly will be useful going forward with what you do in terms of exploitation. So I look forward to seeing how we develop,